kinetic energy is where life gets really interesting. So think of an arbitrarily shaped object which is undergoing a rotation around some axis. And just choose a point on that object. Now that point's going to go around in a circle. So that point's going to be going a certain speed. And that speed is its tangential velocity, v. Now we're going to assume that there are lots of these points. All of these points make up this arbitrary shape. And as you know, I like to use potatoes for my arbitrary shape. So think of little bits of the potato. They're going to all add together eventually. But let's just say I've got hundreds and hundreds of those little bits of the potato. But let's just look at one of those little bits. And that's going to be the ith piece of potato. We use the nomenclature of I for some arbitrary one of those many things. You've seen this in mathematics. So that ith piece of the potato has a mass, m sub I. It has a tangential speed, v sub I squared. And so its kinetic energy is 1/2 mv squared. And what I'm going to do is I'm going to add up the kinetic energies of all these little particles. And when I add up the kinetic energies of all those little particles, I'm going to get the overall kinetic energy of the potato. Well, so inside of my summation, the 1/2 can come out. That's no problem, and that's what I've done here. I brought the 1/2 out. And that leaves the mass times the velocity. But remember from the previous page, the tangential velocity, which is the only speed that I'm worried about here, is equal to r omega. So the ith piece of potato has a distance r from the axis of rotation, not from the center of the potato. There really isn't a center. From the axis of rotation. Because this ith piece of potato is going around that axis. That's where its center of rotation is. And so the speed, v, in the 1/2 mv squared is the same as r omega. And of course I square each of those terms. And so what I'm going to do is I'm going to combine the mass and the radius squared. Because remember, all of those pieces of potato, they all have the exact same angular speed. They all take the same amount of time to go around that axis. Whether they're near the axis of rotation or far from the axis of rotation, their angular speeds are the same. And so since they're all the same, these aren't going to be different for any one piece of that potato. It gets to come outside of the summation sign. And so since it's outside of the summation sign, the summation is only going to care about the mr squared. And so I get 1/2 omega squared times the summation of the mr squareds. But remember, kinetic energy is kinetic energy. So in the linear world, it's 1/2 mv squared, linear mass times linear speed. In the angular world, it's 1/2 the angular mass, which is I, times the angular speed, which is omega squared. And so this part right here is the moment of inertia, the rotational mass, if you will, or the rotational inertia. So the sum of the mr squareds, by looking at kinetic energy, tells us how we discover the rotational inertia of an arbitrary shape. And so the way we do that is we look at where the mass is and how much mass there is there. But notice the r squared. This summation, we've seen that before. When we talked about center of mass, the position of the center of mass was equal to the sum of the mass sub I times the position of each of those pieces, all divided by the total mass. Well, this is pretty much the same, except we're squaring that position, and we're looking at a distance from the axis of rotation, not a position in the xyz. And so how do I find the rotational inertia, or the moment of inertia of the potato? I take each of these little m sub i's and we add them all together. And so I'm going to have a summation of each mass times its distance from the axis of rotation. Be very careful. This is not from a central coordinate origin. It's from the axis of rotation, not from 0x, 0y, 0z. It's from this axis right in here of rotation. And so can you guess how I'm going to do this? I think you can. I'm going to take a little piece of this potato, and it's going to have some mass, dm, and some distance, r, from the axis of rotation. And I'm going to turn this summation into an integration, and I'm going to integrate the position of each little dm, the position squared, and I'm going to add up over all of those dm's. And that's going to get me the rotational inertia of that potato. So the rotational inertia, or the moment of inertia, I'll use both terms interchangeably, is an integral of r squared dm. And so if I'm talking about an axis of rotation here, I'm rotating about that axis, and I just have a point particle, that's really easy. The point particle has a distance r from the axis of rotation, and it has some mass m. And so r is fixed. It's going to come out of the integral, and I'm going to end up with r squared times the integral of dm. But it's a point particle. Its total mass is just m, and so I end up with mr squared. But what if I'm not talking about a point particle? What if I'm talking about something different? Well, what we want to do is we want to start off with something different, but something kind of easy. And so let's think of a ring, just like the ring on your finger, only very, very thin. And so let's think about a ring, and it's going to undergo a rotation about a point in the middle of the ring. And so there's my ring, and here's the axis of rotation through the center of that ring. So it can have a dimension in this direction. We really don't care, but it needs to be thin as far as its dimension away from the axis of rotation. All right, so that should be thin. That thickness of the ring, if you will, should be very thin. So we're going to be looking at a thin ring. We'll look at thick rings later on. All right, so what I'm going to do is I'm going to take apart a little piece of that ring right there. And from the center of rotation, there's going to be a point there and there to either side of that thin piece of the ring. All right, so there's my piece of the ring. There's an angle in here. I'm going to call that angle d theta. So there's d theta. And the ring has got a total angle all the way around, of course, of 2 pi. And I've got a small portion of the mass here. That's going to have a mass dm. And since it's a ring, and it's all equally distant from the axis of rotation, all of the radii, or all of the positions of my dm, are the same distance r from the center of the circle. And so there's a couple of different ways of looking at this. So when I go to do the integral of r squared dm, I see that as I go around from one mass to the next, each time I'm breaking that down into a little bit of a mass, the r's don't really care. And so since r doesn't matter as far as what dm I pick out, I can pick this one, or this one, or this one, or this one. They're all the same radius. So the distance is independent of the mass, and so it comes out of the integral. So I get the integral of dm with the r squared to the outside. Well, the integral of dm is just add up all the masses. And so this is just equal to m, total mass of the ring, times r squared. So for a thin ring, the moment of inertia of a thin ring is just mr squared, the mass times the radius of the ring. The other way I can look at that is I could find a relationship between dm and the angle theta. And what we would discover is that if I was somehow able to change this variable of integration from mass to angle theta, I would discover that no matter what theta I chose, whether it was 0 degrees or 45 degrees or 90 degrees or 135 or 180, they all have the same radius. And so again, the r squared, and it's the same mass per unit angle, all that's going to come out, and I would just end up with mr squared. All right, so a uniform ring is easy. But now let's do a disk. So here's my disk, and it might have some thickness. I really don't care. And I'm going to take the same axis of rotation through the center of the disk, right? And it's going to rotate around. So if you think of a plate and you put the plate on a table and you rotate the plate on the tabletop. So it's rotating about an axis through the center of the disk and perpendicular to the disk itself. There are a lot of axes. I could have a different axis. I could have an axis cutting along the disk like that. But we don't want to do that. We just want to keep it nice and easy. So I have an axis that is perpendicular to the plate, to the disk, and through the center of the disk. I could also have one through here as well, but we're not going to do that now. We'll do that later. So I want to do the integral of r squared dm. Now I want to be smart about this integral. I could choose a little tiny piece of it, and it would be at some distance r, maybe r1, but over here there'd be another little tiny piece, and it would be at a distance r2. And so I'm going to have to find out what are the relationships between all these radii and all these little positions. And that's going to be too much work. So let's find an easier way to do that. I need to pick a small element of the ring with a mass dm. Now a small element can be a little bit of a cube, but it can also be a thin ring as a piece of that overall disk. So imagine, if you will, that I've got a thin ring, and the thickness of that thin ring, it's not 0, but it's going to be really tiny. It's going to be dr. So it's a very thin ring with a thickness of dr. And the radius of that ring is r. And the mass of that ring is dm. Now we're going to call this a uniform disk, meaning that its mass per unit volume is the same everywhere. So it's going to have a density rho equal to the mass per unit volume, and that's going to be a constant. It gets much more difficult if the mass per unit volume is different at different radii or different angles. But we're going to keep it simple. Alright, so I know that the moment of inertia of that thin ring is equal to the mass of the ring times its radius squared. So the moment of inertia of the thin ring is r squared dm. And so that's equal to the moment of inertia of the ring. Now that's not the moment of inertia of the disk. So the moment of inertia of the ring, it's just a portion of it. It's going to have a moment of inertia of di, because it's not the total moment of inertia. But if I integrate this both sides, I'm going to get the total moment of inertia of the ring. I, for the entire ring, is going to be the integral of r squared dm of all of the rings. And so what I want to do is I now want to integrate r squared dm. Now keep in mind, as I go to a different ring out here, if I go to a different ring, and I'm going to go to this one in brown, it's going to have a different radius. And it's going to then have a different dm, albeit still small, but it's going to be different than the black ring because it's got a larger radius. So let's get back to this density thing. Density is equal to mass per unit volume, which is dm times d volume. And since the mass per unit volume is constant, dm over dv is constant. But I can rewrite this as rho dv equals dm. But what is the volume of a thin ring? Well, the volume of a ring is equal to the circumference of the ring, right, the distance around, so 2 pi times the radius times its thickness up and down. And so that might be, let's just call that t for thickness. But then also times that thickness, which is dr. Let's actually change the thickness there to height h. Alright, so think of a tin can, cut off the top of the can, the bottom of the can, then the volume of the can is the circumference of the can times the height of the can times the thickness of the can. But the can is very small in thickness. Circumference times height times the actual thickness of the metal, which is very tiny. And that's essentially what we're doing here. And so R does depend on dm. The brown and the black mass are different for different radii. So the integral of r squared dm, well, that's going to equal the integral of r squared, here's dm right here, so that's rho 2 pi r squared h dr. And so this is 2 pi, oh, that's not r squared, that's just r. 2 pi rho h times the integral of r cubed dr. And so this is 2 pi rho h r to the fourth over 4. And my limits of integration are from the innermost ring, which has a radius of 0, to the outermost ring, which I'm going to call that radius capital R. So I evaluate from 0 to capital R, and that's going to be 1/2 pi rho h capital R to the fourth power, 2 over 4, giving me the 1/2 there. But rho is the mass per unit volume, and so the mass equals rho times the volume, but the volume of the disk is equal to pi r squared, the area, times h, the height. And so rho is mass divided by pi, big R squared, h. So if I substitute that in, I get 1/2 pi times rho, but that's mass, over pi r squared h times h r to the fourth. And the pi's will cancel out, and the h's will cancel out. So notice it doesn't matter what this h value is. The height of the plate is irrelevant. The moment of inertia is the same no matter what the height of the plate is. The formula is the same. Of course, the higher plate will have a bigger mass. And then r squared will cancel 2 of the r's to the fourths. And I'm left with 1/2 mr squared as the moment of inertia of a disk rotated around an axis perpendicular to the disk and through the center. Alright, so what do I do if I'm going to rotate around that disk but not through an axis through the center? Let's draw an axis through the center. What if I want to rotate it about an axis over here? So it's actually rotating around that axis and not this one. Then what do I do? In order to find that out, what we do is we use what's called the parallel axis theorem. Parallel meaning I have to know what the rotational inertia is about an axis parallel to the one that I'm interested in, but through the center of mass. Now that's very important. So this axis right here is the one I'm interested in. Let's make the axis I'm interested in green. So I'm interested in the rotational inertia about the green axis. And what I have to do is I have to find an axis parallel to the green axis that also goes through the center of mass. And that's going to be the black axis here. So I already know for a disk that the moment of inertia through the black axis, so I of the black axis, that's equal to 1/2 mr squared. I already found that just now. But I'm interested in the moment of inertia for the green axis. Now the green axis must be parallel to the black axis, hence the parallel axis theorem. So what the parallel axis theorem says is that the moment of inertia through the green axis equals 1/2 mr squared, the moment of inertia of the black axis, plus the mass of the object times d squared, where d is the distance between the two parallel axes. And of course, if the axes are parallel, the distance never changes. So d is the distance from the green axis to an axis parallel to the green axis. So moment of inertia through the green axis is 1/2 mr squared, the moment of inertia through the center of mass, plus md squared, where d is the distance between the green axis and the parallel axis through the center of mass. So if d were, say, half of the radius, if d equals 1/2 the radius, and it might not, it could be something different, but in that scenario I could write out I through the green axis equals 1/2 mr squared plus m times half the radius squared. So this would be 1/2 mr squared plus 1/4 mr squared, which is 3/4 mr squared. So notice the moment of inertia through the green axis is bigger than the moment of inertia through the center of mass, and it will always be that way because of all the way things are squared here. I've added a term here. So the moment of inertia through the center of mass will always be the smallest moment of inertia about an axis parallel to that value. And this can actually, the parallel axis theorem can be derived through integration. We're not going to do that in this class. But the parallel axis theorem is based on integration. This is really an important aspect of integration, is that remember that integration is a summation. And so what do we do then if I have multiple shapes? Okay, so integration is the same as a summation. What if I have a long rod, a long thin rod with a ball at the end of it? Okay, so I have a long slender rod and a solid sphere. This is really common for like a grandfather clock. And I'm going to have the axis of rotation up here. So there's the axis of rotation. So if we look at our book, we find that if I have a slender rod and I rotate around an axis in this direction, say in and out of the page, then the moment of inertia through that, this is for the rod, is 1/12 mass of the rod times the length of the rod squared. And if I look at moment of inertia through the center of the solid sphere, then the moment of inertia through the sphere is equal to 2/5 the mass of the sphere. The mass of the sphere is equal to 2/5 the mass of the sphere times the radius of the sphere. squared. So what's the moment of inertia of this system, this glued together system, about this point up in here? Well, since it's an integration, we could do this by integration. We definitely don't want to. That must be it's the summation of these two components. And so what I'm going to do is I'm going to say, well, what's the moment of inertia of the rod about this end point? Well, so that's going to be I of the rod is going to be 1/12 the mass of the rod times the length of the rod squared plus the mass of the rod times this distance, parallel axis theorem. But that distance, since it's a long, slender rod, is going to be half of the length of the rod. So L over 2 squared. And so that's 1/12 ml squared plus 1/4 ml squared, which is 3/12, so that's going to be 4/12 ml squared. And so that's going to be 1/3 ml squared. Now that's just the rod. The sphere about this new axis is going to be 2/5 mr squared plus the distance from here to here, so plus m, and that distance is L plus the radius squared. And so what happens then is the moment of inertia of this combined system, if you will, is going to be 1/3 the mass of the rod times the length of the rod squared plus 2/5 m, mass of the sphere, times the radius of the sphere squared plus the mass of the sphere times L, length of the rod, plus the radius of the sphere, quantity squared. So I just add together, because it's an integration, I sum the moment of inertias of each of the components. And that's how I find the moment of inertia of a combined system.